Hello, everybody. Welcome to my presentation about virtual threads and my experience with playing with them, experimenting with them, and implementing them later in a GlassFish server, or implementing support for them. I didn't implement them. It's the JDK team who did it, and they did very good job and still have big plans with virtual threads and threading in the newer future Java versions. So let me try to explain what is it virtual threads and what are the benefits of using them. First, shortly about me. I'm a Java champion, Java user group lead in Czechia, in Prague. I'm also a committer to specifications, developer, and I'm a founder of a company, OmniFish, who supports GlassFish server. So let's start with just basics. Virtual threads were introduced roughly a year ago with Java 21. Since then, almost everybody remembers Java 21 as something that, or a version of Java that delivered the long-awaited virtual threads. There were several other improvements in previous versions of Java, but virtual threads are one of the biggest and also one of the things that people don't know what to expect from, because before we had generics, lambdas, streams, or records, but they were basically language constructs. They changed how we write the code. They didn't have much influence on performance, except maybe streams and lambdas, which allowed us to create functional or use functional constructs and implement reactive programming in a much easier way. And reactive programming itself then helped us improve the performance. But besides that, it's just language features, and they don't don't improve performance. Performance was created behind the scene or improved behind the scenes by garbage collection, improving garbage collector, improving the Java in time compilation. But now we have virtual threads, and why they are important. The big difference to all the previous language constructs or language or Java features that were delivered, you don't get to really use them in your code very often. There is a chance that you don't even use them, because you can use, if you already use executors or thread pools in application servers or frameworks, they do it for you. And usually they just provide you an option, a configuration option, to either enable or disable virtual threads them in your code. But the behavior then is slightly different. Virtual threads work very differently from normal threads, at least to a lot of aspects. So why should we use them? Yeah, the quick answer, and I will get to that, is they are faster. They are faster in many aspects, so you can just improve performance. But coming back to platform threads that are already available in Java, and Java did a very good job in implementing them, so it has a lot of good APIs. First, it supports threads. Not every language out there supports threads. It supports them natively without any library, so you don't have to install additional library to be able to use the underlying operating system threads. Java provides the abstraction for you. You can stay with Java with standard things. It builds also quite a good framework or API on top of threads with executor services, which are there. Many of them are there available for you, and you can just choose the algorithm. Another thing that Java provides is actually a quite clever fork join pool, which is different from many other pools. It provides a different concept and is already built in things like parallel streams. So you don't have to think about how threads are implemented or how threading is implemented in these basic Java concepts. But why they are not so cool? The answer is there that they um, they always go to operating system in order to create a thread, in order to interrupt the thread or interact with the thread. So every time Java needs to do something with platform threads, it goes to operating system, and operating system calls are a bit slower, basically around 10 times or even 30 times slower than just a normal method call. And even switching between threads when Java doesn't do anything, the operating system manages that we run hundreds of threads on a computer, on a CPU that is only capable of running maybe 8 tasks in parallel because it only has 8 cores, and it cannot run more than these tasks in parallel. The operating system manages switching the tasks that are actually using the CPU. And the CPU, when it has to switch from one thread to another and give the execution power, to do so-called context switch. It means it remembers all the states for the previous thread, puts it somewhere aside, then takes the state of the new thread that it wants to run, puts it back into CPU, into the registers, copies all the data, and then it can continue working. And it does it only for a few milliseconds, maybe seconds, then it switches to another thread. So every time when it runs a new thread, it needs to do this context switch. And so that means that when you have 100 threads, it needs to do it maybe not more often, but it needs to do it often, and definitely more often than if you only run 8 tasks, 8 threads on 8 cores, because at that time it doesn't have to switch in between threads. It can just keep every thread running on its own core. And this is an ideal state. But very often we need to run many tasks, much more than we have cores. And then we have this switch, which is, again, operating system's job, and it takes time. Another aspect of threads is that they, for this operation, they need to reserve memory. They reserve off-heap memory, so we don't see that in heap size, but the memory is reserved, and reserving means that threads maybe don't need that memory, but the operating system needs to reserve it and not allow it cannot allow other processes to use that memory. Of course, this is virtual memory, so it doesn't have to be the memory on the system, but you need to have at least some paging memory or swap memory available, or at least theoretical memory. So if the process needs that much memory, it should be available. And there are limits. So you cannot reserve more memory than you have on the system, including swap. And so the operating system will not allow you to create many threads, maybe only many threads, but not really a vast amount of threads. So there is a limitation. Let's try to see what is the limitation, at least on my system. We can illustrate it with a simple program, which is on the slide. We'll try to create as many threads as possible and keep them waiting for 10 minutes. So it means that they will still be there. They will not do anything. They will just eat the memory on the system. And basically, I prepared a program that does it. I will show just the code that you saw on the slides. So here, and it does a bit more because I also have a switch, a command line, which allows me to either choose platform threads or virtual threads. By default, the command the command or the program creates normal platform threads, and I'm using a new API from Java 21 to build virtual threads. I'll make it bigger. And the same API can be used for platform threads. So you have a builder, thread builder, and then you initiate the builder either for virtual threads or for platform threads. So that's the only difference. Then you can use the builder to give the thread a name or some attributes. For some things, this is not so convenient because platform threads have more options than virtual threads. Platform threads can be non-daemon threads. It means that the main application thread can only be platform thread, but virtual threads can be only daemon threads, which means that they will get killed when all the non-daemon threads are stopped. So the application will stop when all the non-daemon threads are stopped. So it means that if you have no platform threads, including the main one, the application will stop and all the virtual threads are gone. With platform threads, you can choose if you want to have daemon threads and non-daemon threads, and by default they are non-daemon, so the application stays as long as these default platform threads are running. So that is a difference. But when you don't care about this and you only want to create a thread, you can use thread builder, and then just with one option, you can either create a thread builder of virtual threads or platform threads. And then we can give it a name, and we start the threads with some task. And yeah. So the actual code I'm doing is, I'm not doing while, but the while is here. The whole block is in while. So I'll create, in every iteration, I create a new thread and wait 10 seconds. And I also count the threads so that I can print. Let me show you how it looks when I run it. First, I will run it without the simple as it is, just run the command, and we create threads. And the speed of creating new threads is slower and slower. So when we create more and more threads, we need more and more time. I don't know exactly why, but I always observed this behavior. And there is a certain state when you reach too many threads, 37,000, and then you reach out of memory error. And I will kill this process because I don't know if I can recover from this by any means, because it means that you basically reserved all the memory, and it's not heap. So the execution that only needs heap memory can continue, but you cannot create more threads. And if you run operations, maybe even if you want to run a new thread, then you can't, because you reserve too much memory out of heap by creating so many threads. The behavior of virtual threads, I wanted to check if I have a chat open, because I'm not able to open the chat in Zoom for some reason. I don't see the chat in case you have questions. Don't know why the window doesn't open. Try to check it later. In case you have questions, I will read the questions later. So now we'll run the same program just with the virtual thread switch, and we'll see what is the difference. The main difference is now I'm able to create much more threads. It's in millions, not 37,000, and I can create as many of them as possible until I hit a limit. And I forgot to limit with heap size. Now we use the default heap size, so we can create a lot of threads. But I wanted to show you how it works when we limit the heap size. With limiting it to 500 megabytes. We have the same speed, but very soon we hit the limits when we need to the Java virtual machine needs to create some memory for the threads, but it takes it from heap. So now it behaves differently when we limit the heap size. Before it was outside of heap, so it didn't matter how much heap we allocate. It was basically limited by operating system. Now the limit is the size of heap, and now there is a different reason we get out of memory error, and that's because first garbage collector tries to allocate more memory, or free more memory to allocate some new memory for new threads, and it can't do that. So it thrashes the CPU. CPU is 100% trying to find some memory. It does it in cycles, and after some limit given by the Java virtual machine, it just gives up and gives out of memory. In this case, you have 100% CPU in the garbage collector. Your process cannot continue because everything, every execution needs heap memory in the heap. So you cannot continue also other threads because they need to create objects, and they will be limited. So in this case, everything basically stops when we don't have enough memory to create a new thread, because the heap is full for everything, not only for creating new threads. But the end result is more or less the same. The process cannot continue and it's killed, because also in this case, before, when we ran with platform threads, the operating system basically killed the process because it's out of memory. So it's only different the reasons, but the end result is the same. You run out of memory and your process dies. But with as I showed you before, if we remove this limit or run it with a bigger limit, we can create much more threads, and we can reduce the risk that we eat so many resources, or that our process is killed. The other difference is that for platform threads, this memory is just reserved. So we run out of memory. Also, this is how it looks. Also, when we don't need it. This is the memory allocated for threads and used for threads. This is just a random picture, but just to allocate, just to show you. By default, each thread needs 1 megabyte of memory reserved. But in reality, it uses it only to store the stack and variables on the stack. And most threads will just use like 10% of it, or 25% at most. They will very rarely come close to 1 megabyte, only when you have a very, very long stacks, and for some, and it's also only for some threads, not for all of them. So in reality, you reserve much more than you need, but you can't do otherwise, because the same limit is for every thread. If you reduce it to let's say 100 kilobytes, there might be some thread that needs more, and then you have an exception without a reason, because it just needs some more kilobytes to store the biggest stack. So to run everything smooth, we rather reserve more than we need, instead of reserving less than we need. But with real threads, only this red thing, only this amount of memory is actually used. Maybe virtual threads need a little bit more memory, so well optimized than if you just allocate memory or store memory outside of heap. Everything is a Java object, and it has its own overhead. But still, it's very close to the red thing of platform thread, and you don't need to reserve so much memory. So that's the difference. With virtual threads, you run out of memory only when you really run out of memory, and you cannot use more because it's limited by the size of the heap. Now, there is one answer to the drawback of platform threads, to the drawback that they are slow. They are slow to create and slow to switch between them. Traditional approach is to limit their number. And it's a practice known as thread pool, so that you pre-create threads and then keep the threads for different tasks. So when they're finished with one task, they are still kept. And when there is new task, they are assigned this new task. If there are no more tasks for the thread is just kept there for a while. And then if you have too many threads waiting for a task and there's not so much work, some of the threads are discarded, but still some are kept in case some more task needs to be processed. So this is a good approach. You can get very good performance with this, but there are some problems. Yeah, the limiting. If you also limit the number of threads, you can also prevent the out of memory error, and that is also a good practice. And that's what usually thread pools do. They don't create more threads than allowed, and then the tasks are just waiting on the queue for a new thread that is available. So there are two things. One is to reuse the threads, do not drop them and create again. And another thing is to keep the amount of threads small, or reasonably small, not too big. But as I said before, it's better to have just as many threads as you have CPU cores, or a very similar number, not like 10 times more, because then you have too many context switches, and that is also slow. So it's better to have some thread pool that is close to this number of CPU cores. But with platform threads, that's not really possible to do, because you very rarely, it's very rarely that it will be enough for you to have so many threads. It will be less performant than actually creating more threads, because a lot of tasks are blocking, are waiting for I/O, and if they keep one thread and can be paused by a task that operates on I/O, then no other task can do anything. So you would rather increase the amount of threads to allow more tasks work on, and it's more performant than avoid constant context switches. Another problem is, even if we have thread pools, there are things more an edge case, but they can happen. If you use thread locals, and many frameworks do use thread locals, even in your code, I believe that everybody used at least once a thread local. Thread locals by default are removed from a memory only when the thread stops. And if we use thread pools, threads are reused, so they are not very often stopped. It means that if you don't remove the thread local, it will keep being in memory until at some point you have too many threads and too few tasks, so some of the threads are removed, and then the thread that keeps the dismiss or non-leaked thread local will be dropped, and the thread local will be removed from memory. Good thread pools sometimes stop threads and recreate them to avoid this, because if you have one thread running for hours, it may increase the amount of thread locals that are kept for the thread. So it's good to recreate the threads sometimes, but not very often. Another thing is that if you have a process that relies on the same thread local, so same code, but the code is reused for another request, if you forget to clean the thread locals, you can have state from the previous execution, and that's even worse, because it may impact the outcome of the computation. So, is there a better way? With virtual threads, yes. With virtual threads, you don't need to create thread pools. Yeah, they are fast to create, they are fast to switch between them, so you don't need to limit them that much. I would still limit the number of virtual threads, but not because I want to avoid context switches, because they are minimal, but in order to avoid out of memory in case the virtual thread still, or the process that runs on the virtual thread still needs some do some computations. It needs to allocate some memory, read data from database, do something with the data. If you run millions tasks like that, you can with virtual threads, but they will run out of memory because all those tasks need some memory, and then it's better to a certain number of virtual threads, but ideal solution might be to have some mechanism to watch for free space in a heap, and if you're running out of heap, then not create more virtual threads or not allow a task to continue on a virtual thread, just to limit the number of tasks. But this is not limiting the number of threads, this is limiting the number of tasks that are running in parallel, which is different. Here with virtual threads, we don't need to care about number of threads, only number of tasks running in parallel and the amount of memory they need to complete. So this is what I showed you already, how to run virtual threads and what is the difference. You can run a lot of them, and depends on the amount of heap. And another thing is, I told you that they are faster. So this is where we come to another experiment that I did when I worked on implementing virtual threads in a new version of GlassFish. Still not in the current GlassFish 7 version, although I will be using GlassFish 7 version because GlassFish 7 allows to plug in a thread pool, a custom thread pool. So that's what I did, but it's not out of the box. I created a thread pool separately from GlassFish and then configured GlassFish to use it, and I dropped the thread pool code into GlassFish as a module, or on the cast path basically. What I found out when I compared the same scenario, ran the same performance test, I saw difference between when using platform threads for the HTTP request and virtual threads. And with the same code, just with the different thread pool, the thread pool that actually just creates a new virtual thread for every request and then throws it away, you could think that when I create a new thread and then throw it away, it will be slower, but virtual threads are actually faster. And the speed comes from two reasons. At least that's what I think. One is that creating a new thread is cheap and it's completely negligible. So it doesn't slow us down, or very marginally. So it doesn't matter if I reuse the thread or create a new thread every time. With platform threads, we didn't have that. If we did that with platform threads, we would have maybe 15% performance degradation. But with virtual threads, it will be more or less the same. So we're still on 0, but this additional 15% increase, I think, is because we reduced context switches and in virtual threads. With virtual threads, we can create a lot of virtual threads, but platform threads are being executed. And this is how we get to how virtual threads work. They are plain Java objects, and they store stacks in a heap. I already explained that. But they execute on platform threads, with this kind of a twist. We need threads to execute threads. Yes, we do, because platform threads are basically mapped to operating system threads and to CPU cores. And JVM or any process on the operating system cannot otherwise schedule or run instructions. It needs to run in at least one thread that is supported by operating system, and that then tells CPU what to run. But what JVM does, I think I have a picture for it, it creates a lot of virtual threads which are just Java objects, and they point to instructions that should be executed. And Java Virtual Machine then decides which of these threads or which of these threads is executed on a real platform threads. But the point is, it only creates a few platform threads. They are called carrier threads, and they are basically a thread pool. One thread pool that is created by the JVM, which contains real platform threads, not virtual threads. And it reuses these threads for running different virtual threads. One carrier thread, one platform thread, can run one virtual thread, later can switch to another one, and later another one, later do the same as before. So it's just like executor of the tasks defined in virtual threads. Let's imagine a virtual thread as just a pointer to the code, to the next instruction that should be run. And when it's executed, the pointer moves to the next instruction. But the carrier threads actually do the instruction. So they get the pointer from the virtual thread, and they execute the instruction. Then they read the next pointer, execute the instruction. So they are the executors, the real workers. Virtual thread is more like a recipe to what needs to be done. And the same platform thread can do many, or can follow many of these virtual threads, many of the recipes at the same time. And the trick is the virtual machine detects when one virtual thread will be blocking when it executes blocking instructions or some I/O operation from network or from a file system, or thread sleep, for example, also counts. Anything that would block unnecessarily triggers the operation, the blocking operation. So it will normally go to read a file from a file system or read data from network, but at the same side, and we'll tell the carrier thread to run a different virtual thread. And when it comes that some carrier thread is free to, or chooses some other virtual thread, it may choose the previous virtual thread that was waiting, but only after it already received the information or stopped the I/O operation. It can continue with another task immediately, so carrier thread will pick it up and continue with processing of this virtual thread. So virtual threads ideally occupy carrier thread only when they execute actions, but as soon as they initiate some blocking operation, they are removed from carrier thread, and another thread that is ready to execute some action continues on the same carrier thread. That's basically why it is more performant, I believe, because with just fewer real threads, there are much fewer context switches on the CPU between them. And the JVM creates only as many virtual threads as there are core CPUs. We can configure these on command line when we start the JVM process, but most of the time we don't need to do that. Because we don't need many carrier threads. We only need many virtual threads. And when we have just few carrier threads, we reduce the context switches. And the context switches between virtual threads are very fast, because it's basically JVM does monitors, runs some Java code, probably optimizing C if it's OpenJDK. Maybe if it's ground, it's just pure Java code. But it's pure in JVM. It doesn't need to go to the operating system to find out that one virtual thread is going to execute a read operation or I operation. It just basically instructs carrier thread to continue executing a different virtual thread. And that's the whole context switch. It doesn't need to go to operating system, doesn't need to go to CPU, doesn't need to replace registers in CPU. It just continues. So now what I did with GlassFish, I will briefly show you how I implemented this, but basically I wanted to show you the outcome, what I achieved just by using virtual threads on some demo application. So I created an application that just simulates some not so fast, but also not so slow process. It's an application that simulates some I/O operation, and every request just consumes or takes around 100 milliseconds, more or less. There is some random around it, but it just simulates how it would work if it really went into database and retrieved some data, provided that the database operation is not very slow. It's just a simple application. In reality, one request could take more than 100 milliseconds, but it's not ideal. So if we have longer running requests, the outcome of the test would be different. But this is just to simulate some behavior, including bigger stack trace. So to simulate that virtual threads put things, put stack on a heap size, and we need to create some objects to remember the stack. So I did all these. I will show you the code later, but first I wanted to impress you with the results. So when I do a simple demo, I already started both versions of GlassFish, one with the platform threads, one with virtual threads. And I use a tool called Bombardier to create a lot of, in this case, 12,000 threads or requests. Threads are on the server, but I create requests, HTTP requests to GlassFish. And this tool keeps 12,000 requests at the same time. So it creates 12,000 requests. When a request is finished, a response comes, it will create immediately a new one to keep 12,000 parallel requests at the same time, all the time. So when we run it on port 8080, where I run the version of GlassFish without virtual threads, let's measure it for 10 seconds. How fast it is. The same application, just with platform threads. And basically the default configuration of GlassFish. There's one tweak in GlassFish to allow more HTTP requests at the same time, because usually this is limited to, I think, 1,000 or 2,000. And we have, in this case, 12,000 on average. This is sounds like a not a very good number, but remember, this is not a benchmark for the HTTP engine. I have an application that actually it takes around 100 milliseconds every time to process, running on Zoom and screen sharing everything. That makes my CPU around 2 or 3 times slower. I can run it again. Maybe we'll get better results, because usually when I run it again, it seems that Java just-in-time compiler makes a good job or caches some things, so the results are better. Not in this case. So okay, so it's around 12,000. Then the only thing I will do, I will run the same thing against GlassFish, which runs the same application, same thing, same logic. I would expect the same output, but it uses virtual threads, the virtual thread executor that we created for GlassFish. And let's wait again. And now we have almost double the speed. I can run it again. In reality, I don't know what is the actual difference, because I haven't run like thousands of measurements, but always when I run the measurements, I see around 15 to 30, usually 30% performance increase just by running virtual threads. So, and that is every time I do the comparison. So the virtual threads are always faster, always process more requests. And that is a hint that virtual threads really improve performance of the application. Maybe not for every application, but I think this applies for 95% of applications. When you just run thread pools on virtual threads, you would immediately have performance increase because of the reduced amount of context switches between threads, mainly. So that's for the demo. I can show you briefly the code. Okay, for that, let me go to projects. So I have a simple servlet deployed on GlassFish. And what it does here is not important, but basically do-get method, the processing of the request, runs this code. And in there, I have two methods. Run in deeper stack, which means it will, we'll show, it will basically run recursion itself a couple of times, in my case 100, and it creates 100 nested calls to the same method. But this is at least to simulate calling like 100 nested methods or 2 arguments. So it is not a real life demo, but it's closer than just not doing this. I can if I post it somewhere here, I would have maybe 20, 30, 50 nested calls, depends on when I break it. But it wouldn't be just small, just one method called here to get. Another thing is that GlassFish itself calls methods to process the HTTP request to go through the servlet engine. So even GlassFish creates a lot of method calls nested, but I wanted to increase it because also usually an application does another quite significant amount of nested method. And at the end, when I have 100 methods nested, I call this, and this basically just does thread sleep. And this yield is not important because thread sleep, basically for virtual threads at least, does the same thing. It will schedule another virtual thread because sleep is a blocking operation also, and it does also the same thing as other blocking operations on virtual threads. It will sleep the current thread for some amount of time, and it will schedule another virtual thread on the same platform thread. This random.
Ondro, as we're wrapping up
Yes.
on time, there's some questions located in the Zoom chat for you.
Okay, I wanted to open the Zoom chat. I don't know where's the window of. I'll try to find it because I have a lot of windows open, and I don't see the chat. Maybe I will not need to stop screen sharing to find the chat window. Bear with me, I'll try to stop screen share for a while. Where's that chat? Yeah, now I see it. Okay, so I can start screen sharing again, and I see the chat window. I hope it stays there. Okay. Okay, so which operating system do you use for demo? Linux or else? Question from Alexander. I use Linux for this demo, but I don't think it really matters. The difference might be in number of platform threads we could create. This is probably some configuration in the operating system because I always hit the same number, even if I have, like, maybe it's by the amount of memory I have, including a swap, but it seemed like some configuration option. But I believe it would behave very similar. But I use Linux. Second question, nice, but I miss a clear indication that we created too many threads. Any way to diagnose this with the JDK troubleshooting tools? Okay, yeah, this was just a short demo. You mean probably the first demo I did with just creating a lot of threads. The JVM itself is not clear, especially in when we have platform threads, and also for For virtual threads, you wouldn't get the message that you created too many virtual threads. In both cases, we have just out of memory. The indication would be with virtual threads, there is a quite clear indication when you run out of heap space. So when you monitor heap size and when you come close to it, like 90% of heap is filled, you will see that you probably use too much memory. And if you invoke garbage collection and the memory doesn't go down, it might be also a different issue of your application or anything causing memory leaks, or maybe you just need more memory. But it's always a good indicator to monitor the amount of memory used, and when you get close to the maximum heap size, you are in trouble anyway. So it might be because you created too many virtual threads. It might be because you just need more memory, but you would discover it, and then you can have a look at number of virtual threads, but or I would more like have a look at number of parallel tasks, because the problem with virtual threads is that the OpenJDK or project didn't want to output information about virtual threads into thread dump. So by default, if you don't enable some option in JVM, you don't see the diagnostics of virtual threads. I want to thank you everybody for watching, and see you sometime maybe at the conference or virtually. Just reach out to me if you have any questions. I'm there on the internet. You can find me definitely. Thank you.